Last time we have seen sample space and events. In that chapter, we have discussed random experiment and concept of sample space. Also, we have seen different types of sample space. And after that, I talked about event and various types of events. At the end of the chapter, I discussed different type of examples which are expected to ask in examination. Today we are going to start the next chapter under the heading of elements of probability. Let us see the first definition for elements of probability as classical definition of probability. The name probability is not new to you. It is already introduced in your school mathematics, I can say 11th and 12th. Probability is a mathematical terminology which is synonymously labeled as a percentage. When we calculate the percentage, we multiply 100. So if you drop the quantity multiplier 100, the rest part is nothing but your probability. So firstly, how to calculate the probability? That approach is named as a classical definition of probability. I will define first and then we'll go ahead. Let the random experiment has small n mutually exclusive and equally likely outcomes. Let among these m outcomes, are favorable to event A. Then the probability of occurring an event A is bracket m divided by n. So this is a simple definition of classical approach to probability. Let us see what the definition says. We have random experiment and that experiment has n outcomes. Out of these n outcomes, m are favorable to your event. So by using this information, we calculate a probability as a ratio of two positive numbers. M is a favorable outcome, small n is a total outcome. So this approach is named as classical definition of probability. To apply classical definition in the real life, you have to check the nature of outcome of random experiment. Outcome should be mutually exclusive and they should be equally likely. Under these two conditions, you can apply classical definition of probability. You can write the definition by the notational form. P bracket A, you can read as probability of A equal favorable outcomes to A divided by total outcomes of experiment. So it is a simple ratio of two positive quantity. m divided by n. So this square you have to remember as a classical definition. But in examination, if they ask you define a classical definition, writing this much is not enough. You have to elaborate like this. First sentence says, random experiments should provide mutually exclusive, that means disjoint, and they should be equally likely outcomes. If these two conditions satisfied, they can apply classical approach. Otherwise, we can't. Let us put certain remark on this definition and then we'll go ahead. Remarks. In my definition, small m and small n both are non-negative numbers. And that is why chance of getting any event always non-negative. How I put 0 here equal to 0? There is a possibility sometime outcome is not favor to the event. So m may be 0. But can n is 0? Answer is not. Because n indicate total outcomes of the experiment. When you perform any experiment, it has minimum one outcome. So denominator of this definition, never 0. Numerator may be 0. There is a possibility nothing is favorable to the event. So 0 divided by this, sometime probability may be 0. And that is why first remark says calculation of probability never negative. That you have to remember. Remark number 2 says, in this ratio, m is a subset of small n. So m always smaller than denominator, because m coming from n. And that is why remark number 2 says m less than equal to n for any event. So we write chance of getting a less than equal to 1. Let us combine remark 1, remark 2 together. So 1 and 2, if you apply together, you get this square bracket. You get a rectangle. And what this rectangle tells you? Probability for any event always lies between 0 and 1. So you have to remember limits of probability, never below 0, never greater than 1. In other words, calculation of probability always fraction. Let us go for third remark, probability of A dash. I told in your first chapter, A dash is a complement. If I want to write probability of complement with the help of this concept, m is favorable to A. Similarly, I have to write probability of A dash. How many favorable to A dash? Look the tree diagram. Experiment has total outcome n. Out of n, m are favorable to A. So naturally, the remaining, this minus this, they are favor to complement of A. So if I ask probability of A complement by classical approach, it is the ratio of this number with this. And that is why I wrote P of A dash equal n minus m divided by n. Now by making a simple algebra, I divide this numerator by denominator. n divided by n become 1 minus m divided by n. Again, you can see m by n is a classical definition. So it is replaced by PA. So you got the relation between chance of getting complement in terms of chance of getting original event. If I took this minus PA on the left side, you get one result. The result is probability of A plus probability of complement always 1. That you have to remember. So this is nothing but classical definition of probability with corresponding remarks. Remarks are very important to solve multiple choice questions. Let us proceed ahead. We'll try to understand classical probability with some examples. I wrote near about 7 examples to understand classical approach. But the difficulty level will be keep on increasing as I will explain problem one by one. Let us try to understand example 1. A pair of unbiased dice are rolled. Find the probability of getting event number 1, even faces on both dice. Number 2, number 3, and number 4. Let us try to understand what question says. We have dice, but pair of dice. That means 2 dice. And what is the nature of dice? Unbiased. So what this word? This word is important to provide equally likely outcomes. If this word is dropped, you cannot apply classical probability. Let us see how this question will be solved with the help of classical probability. Example 1. Start with random experiment. Rolling of 2 unbiased dice. In chapter number 1, I told you, if you throw 2 dice, sample space has 36 elements. So for this random experiment, I can write sample space omega equal the curly bracket 1 1 1 2 dash dash 1 6. This first element is for first dice. This is for second dice. So I observe the top face of both dice, and then I record how many dots are there. So you will have 1 dot on first die, 1 die on second die, 1 die on first die, 2 dots on second die, and so on. So this experiment has totally 36 elements. After having this, we define the event. Event number 1. I told in chapter number 1, events denoted by any capital letter. Suppose I take A1. I define event getting even faces on both dice. So from this omega, I pick up those elements. Those are satisfying my condition of the event. I want even faces on the both dice. So my element will be 2, 2, 2, 4, 2, 6. Another possibility is 4, 2, 4, 4, 4, 6, Next possibility is 6, 2, 6, 4, 6, 6. That means out of 36 elements, only 9 elements favorable to the event A1. Therefore, by classical approach, chance of getting this event in the experiment is 9 upon 36. It is simplified as 1 by 4, and 1 by 4 is nothing but 0.25. If I try to interpret this number, it says if you repeat experiment 100 times, there is a chance 25% to get this event in your experiment. Now what I did, I kept remaining 2, 3, 4 as a homework because it is not that difficult. So I will advise all the students solve this question bit number 2, bit number 3 and bit number 4 by using this way. That means for second event, define A2. Get element of A2, write M, and write the formula of classical probability. Before going to next example, I will tell you what are the steps to solve the problem by classical probability. Step number 1, you should begin with random experiment. According to the question, put the random experiment on the top. After that, if you are able to write omega, you write it. Sometimes it is impossible. If it is impossible to write omega, you get the value of small n. That indicates total outcomes of experiment. Step number 1, random experiment to be written. Step number 2, get the total outcome of the experiment. Step number 3, define the event according to question what is asked to find. If possible, write the element of that event. Otherwise, get favorable outcome for that event. It is a step number 3. And step number 4, use a classical definition formula, favorable outcome divided by total outcome. So any problem of classical probability solve by using 4 steps. Step number 1, write a random experiment. Step number 2, find total number of outcomes, define the event, and apply the formula of classical probability. Let us proceed ahead for next example. Question number 2.